Hello, my name is Dror Regev. Welcome to this session about power amplifier device sizing and gate biasing. So usually one of the first steps when designing any circuit, but definitely a power amplifier, is device selection. So we based our explanation so far about the PA on a common source transistor, but we didn't pay enough time to how we choose the transistor. And we know already that if we want to deliver some minimum power out of this transistor, we will need a minimum current or current swing from this transistor. So the IDVD description of this transistor needs to support the current levels that the transistor needs to be able to push or to drive into the load. And we need to make sure that we take a wide enough transistor such that these currents will be possible to drive. As a rule of thumb, we will usually try to choose the smallest transistor we can that is able to drive the current that we need. We have mentioned before that we are designing a linear PA, Class A PA, and we have mentioned, we didn't explain it that much, but we have mentioned that GM needs to be constant over the input VGS range. So here we have a common source transistor. We already chose the size of the transistor such that it will be able to drive the currents that we need. However, how do we bias this transistor? This is something that we are going to cover in this slide and the next slide. So we already introduced the idea of a load line. So here we can see the load line. And we see the IDVD curves again. This is simulation of this transistor, DC simulation. And we see that the VDS is changing. These are the different VGSs. And our AC operational points are along this load line. So we have this IDS current with that VDS and so on. And this is a dynamic load line, so we need to make sure that when we drive the GM, it needs to be not the small signal GM that we have considered when we talked about LNA, but the GM along this dynamic load line. That's what we are going to do in the next slides. Just as a reminder from previous sessions of the seminar, we have the simplified expression for long channel transistors for I drain, which is somewhat dependent on VDS, but mainly dependent on VGS. If we look at the graph, so this is VGS, now it's ID versus VGS. In the previous slide we saw ID versus VDS. We see that except this bottom line where the transistor is not really saturated, all the other lines show really that the correlation to VDS voltage, here we have the different VDS voltages, is weak, as can be seen also in this expression, even though it's just a simplified expression. But there is some dependency and we need to account for it to have more accurate calculation of the GM later on. For a large signal GM calculation or derivation, we are looking at the ID versus VGS along the load line. So this is the VDS along the load line, and we need to remember that VDS is not constant because at AC it is changing with this factor. Actually this K was calculated before. It's not really a constant, but it is GMRL. And assuming the GM will be constant, it will be constant. Anyways, we drive this current here in green versus VGS when we account for VDS changing as well with the VGS. And the only thing we need to do after we have the drain current, if we want to get the GM, is to derive the drain current by VGS, and then we get the GM that we see here in red, where this is the large signal GM. So here in the middle we can see the small signal GM, and the large signal GM is described here. Of course, if we want to have a linear amplifier, we want the small signal GM or the small signal gain to be very close to the large signal gain. And this is possible in some range of the VGS, the input voltage to the amplifier. So in this area we can assume that we have a constant GM, even though it's not constant, but it's relatively constant. And of course, when GM starts to drop, we get into saturation, and this is where the LNA is not linear anymore. If we look at the current, we can see that the current graph is really almost linear in this region. This is the area where we say the GM is constant or relatively constant. Optimal gate bias will be the range where GM is relatively constant, so it will be in the middle of this range, or will be chosen such that this range will be as symmetric as possible. So we have sinusoidal VGS input around this VGS DC voltage. And this will be the operation point we will find, we will choose for linear behavior of our PA. A couple of papers and also a few books are trying to linearize amplifiers by introducing nonlinearity in a way that will compensate for the original nonlinearity of the transistor. So if we assume that we have some parabolic behavior for the GM, the original GM, and this parabolic behavior caused some nonlinearity because we wanted our GM to be really constant for the range of input voltage over VGS input. If we introduce another nonlinearity which is actually complementing the original nonlinearity to add them both and to get a constant GM, this can help in linearizing the performance of the power amplifier. So a schematic way to do it is to take the original PA and just connect another, the original transistor, and connect another transistor in parallel. We need to make sure that they are in parallel in AC, and this is the capacitor that enables that. Each one of them will be biased at different VGS. So the original one will be biased in a VGS that will give us this parabolic behavior, and the compensating transistor is supposed to give us this behavior, and of course the sum will be relatively constant. However, this behavior is easily achieved in balanced or symmetrical designs rather than single-ended designs. It's not very easy to find this performance in a single-ended design transistor, but it is achievable, and it's being employed. This linearization technique is being employed in differential or symmetrical PAs. Thank you for joining me on this session about PA device sizing and gate biasing. Hope you have enjoyed it, and you are most welcome to continue to the next tutorial of this seminar.